Welcome to Similar Triangles and Related Rates. So before we get into the related rates component, let's just do a quick review of similar triangles. So recall, two triangles are said to be similar if they have their angles all have the same measurement, right? So if the triangles have the same angles, the triangles have the same angle measurements. So you usually have a smaller triangle and then a slightly larger version of the triangle. So the angles match. One's just a larger version of the original triangle. And if we say, look at the corresponding sides, I'm going to label one side with lowercase a and then the corresponding side capital A on the larger triangle. We have lowercase b and lowercase c for our other two sides, corresponding sides capital B and capital C. These triangles were meant to actually match. Sorry about that. Right. If triangles are similar, then their sides are in ratio to each other. So we get that little a is to capital A, as little b is to capital B, as little c is to capital C. So we have an equivalence. The small side over the large side is equal no matter which side pairing we take. Right? And what comes in particular in handy is note if we have one triangle inside of another, as long as the so if we have one triangle built inside of the other, as long as the two sides, as long as the side that's inside is parallel to the side it's replacing, the triangles are similar. So as long as these are parallel, right, then we get that this inner triangle is similar to the outer triangle. So this comes in handy with related rates. We often have situations where essentially we have an inner triangle inside of an outer triangle, and it turns out we just have it turns out we just have similar triangles, right? So for example, if we have a water tank in the shape of an inverted cone that is currently being filled with water at a rate of 0.1 cubic meters per minute. And let's say that the inverted cone has a height of 10 meters and a top radius of 5 meters. We could ask, at what rate is the height of the water changing when the water level is at 6 meters? So if we do our first step for related rates, as always, just to understand the problem. So here we are looking at an inverted cone of height 10 meters, radius 5 meters. So we essentially have an upside down cone. Okay. And it's filling with water. So we have water inside, and that water level is going up, right? And we're pouring water in, probably through a pipe, right? So we have a pipe with water coming out, going into our tank. So we need to identify known symbols and what we are looking for. So a couple pieces of information. This water level is going to have a height h, and the water level will also have a radius r. And then our overall, we'll have a volume of, and then a volume equals V. So V equals the total volume of water. In the tank. We will set T equal the minutes from now. Or just T equals minutes because we're looking at cubic meters per minute. So we know that the water is flowing in at 0.1 cubic meters per minute. And we want to know how the height is changing. So again, we want to know how the height is changing. When the water level is 6 meters. So the next thing that we should do, or step 2, is we should identify the known symbols and what we want to know. So the pieces of information we have, we know that the volume is changing at a constant rate of 0.1 cubic meters per minute. So the rate of change of volume would be how volume is changing per unit of time. So dV dt is equal to 0.1. Right? And it's filling, so it'll be a positive 0.1 since the tank is filling. What we want to know is the rate of change of height when the height is 6 meters. So essentially, we want dH dt, that's our rate of change of height, when h is equal to 6. So this is all the information that we were given just about the water level. We know stuff about the tank as well. That will come into play when we go to write our formula. So our step 3 we have find a formula that relates the variables. So in particular, we need a formula that relates V and H, since those are the two things we're working with, what we know and want to know. So in particular, we need a formula that relates V and H. So note the water itself is a cone. Right, so the water itself is a cone of height h and radius r. Right, so the water forms a cone. And so we can use the volume of a cone. So V equals the volume of the cone. And the volume of the cone is 1/3 times pi r squared h. So we have a formula. Unfortunately, this formula also has r. Right? But this formula also involves r. So this is where similar triangles come into play. So if we look at our cone, the large cone with the water level inside, and we specifically focus on that right triangle with height through it. So we'll focus on this smaller triangle here inside of a large triangle. These triangles are similar. So if I make the large triangle bold, sort of around that blue triangle, right, we have similar triangles. The blue triangle has height h and radius r. The purple triangle has height 10 and radius 5. So essentially we have a capital H equaling 10 and a capital R equaling 5. So what we get is that R is to 5 as lowercase h is to 10. So our little r over 5 The small radius over the big radius should be equal to the small height over the large height due to our similar triangles. So this tells us then that R is just 5/10h, otherwise known as 1h/2. So what we get then is we have that our volume is equal to 1/3 times pi r squared h is actually 1/3 times pi times h/2, that entire h/2 squared, times h, otherwise known as 1/12 pi h cubed. So now we have a formula that relates v and h only. From here, we can move on to our next step. So step 4, we differentiate with respect to time. So we take the derivative with respect to time of v, set that equal to the derivative with respect to time of 1/12 pi h cubed. When we take this derivative on the left, we simply get dv dt. On the right, 1/12 pi comes along for the ride. H cubed, we would go to times 3h squared, and then chain rule, we would have to multiply by dh dt. So we get that dv dt is equal to 1/4 or pi/4 times h squared times dh dt. For step 5, for our step 5, we have plug in the known information. And solve for what we want. So we had dv dt is equal to 0.1. We want dh dt when h equals 6. So we have the equation dv dt is equal to pi/4 times h squared times dh dt. So we know this dv dt, 0.1, we'll just swap out for dv dt. We know that h being 6 should swap out for the h in h squared. So we have 0.1 is equal to pi/4 times 6 squared times dh dt. So this is 0.1 is equal to 36 pi/4 times dh dt, or 0.1 is equal to 9 pi times dh dt. So we get that dh dt is equal to 0.1 over 9 pi, which is approximately 0.0035. And then step 6 was to put this back in context. So put the answer back in context. And make sure the answer makes sense. So dH dt equaling 0.003. Or 0.0035 was the rate of change in height. When h equals 6. So essentially what we have, height was in meters. Time was in minutes. Right? So we have the water level, or when the water level is 6 meters. The water level is rising at a rate of 0.0035 meters per minute. Right? So thinking about, does this make sense? Well, it certainly makes sense that the water level is rising, right? Since we're adding volume, the water level should rise. So note, positive rate makes sense. Since we're adding volume, or since we're adding water, the water level should rise. And so that's one of the easiest places to catch a mistake, is if you notice that the sign doesn't agree with what should be happening. And then make sure that your units are the correct units given the symbols we're working with. So that is a similar problems or similar triangles related rates problem.